All right, we have finished a lot of section 3.1. Last time we talked about the general behavior of the graphs of polynomials and um, no sharp points and things like that, and the fact that um, polynomial graphs um, tend to, at least for simple cases, the even graphs all have the same basic shape, and the odd graphs all have the same basic shape if the sign in front and if the leading coefficient is the same. Um, if you have one term, once you start adding multiple terms, then the graph starts to change in the middle quite a bit. So we went over that. A polynomial can't have infinite number of zeros. It has to be factorable. Things like that. So I just want to kind of recap that, and then we can move on to the last little bit uh, of this section. This is actually a big section. We have to cover division of polynomials. I like to say that polynomials are kind of like the integers of the function, the set of functions. You can divide them, you can multiply them, and you can construct other functions from them in a similar way how you would construct other numbers from the set of integers. Uh, you can get rational numbers from integers. You can get rational functions from polynomials. Um, so and then you can, an infinite sequence of, um, you can maybe construct from an infinite sequence of rational numbers, you can get an irrational number, like pi, and then you can also get an irrational or maybe a transcendental function. I think you can get them from just an infinite sum of polynomial terms. So, anyways, probably not that interesting what I'm saying right now, so let me just move on to the actual topic at hand. So we have the general definition of a polynomial, again, is anything that can be written this way. On a lot of the quizzes, I saw you guys, I asked for your best definition, and what you did is you gave me an example. What I was So you would give me p of x is equal to like ax squared plus x or something like that, or maybe p of x is equal to 3x plus 4, and these are examples of polynomials. This is a quadratic, this is a linear function, but and so I gave you some credit, but the I was going for a general idea, and you could have written, one of the students wrote very well in English. A polynomial has these properties. There's no negative powers, there's no fractional powers, things like that. That was good, and I think that gave that student full credit. But just to write examples wasn't quite enough. You needed to be able to say, it could be, this is the most general definition. Or even if you would have forgotten maybe the coefficients, I would have understood that you understand they can go on for as high of a number as you want. So something like p of x is equal to x to the 100 plus x to the 37 plus 2. That's a polynomial. Okay, so the crucial thing about polynomials is that they are functions of x where the power is a positive exponent. So I wrote some examples here. Another example might be f of x is equal to 3x cubed plus 2x plus 1. Another example, again, let's write a linear function x plus 5. So this is a linear graph. This is a cubic function, which may go something like that. Whoops. I want to make sure I'm being mindful of the camera. This would be a quadratic function here, x squared plus 6x plus 2. Maybe it's going somewhere like this. Okay? Alright, so these are examples of polynomials, but notice something. They all have powers that are positive. And even this last number here, like 5, the 5, even though it's by itself, still has an x there that we don't write because it would be x to the 0 power, and anything to the 0 power is 1. This 1 has an x there that we don't write. There's certain things in math that you don't write it because it's redundant. Some people get upset because, like, when you first start learning to combine like terms, you might have something like 5x plus x equals 6x, and that'll frustrate students because they're like, well, where's the 1? Well, we don't write the 1 because it's redundant. You don't, 1 times anything is equal to that same thing. So you don't write 1x because it's just x, so there's no need to write it. So you're just conscious that it's there. Similarly, there's an x to the 0 there that we don't need to write. And that's why this, something like f of x is equal to 7, that is still a polynomial because this is an integer exponent that's not negative. But you don't write it because it's redundant. So a polynomial is anything that can be written this way where the leading coefficient's not 0 and it is a positive exponent and I'm sorry, integer exponent that are positive. Alright? So something like, and you guys got this right, x to the negative 2 plus 4 is not a polynomial. Something like x to the 1/2 minus 3 is not a polynomial. And then if you look at the graphs, we remember we got some intuition already about what the graphs of polynomials should look like. They're smooth, they're continuous, smooth meaning no sharp corners. So this is smooth maybe. It would look something like this, I think. Like that. Actually, that I might not, more like this maybe. But the point is there's a break in the graph. There's an asymptote right there. So it's not smooth. X to the 1/2, that's a square root function. Minus 3, it's shifted down, so it's going like that. The issue there is that the domain is not from negative infinity to infinity. But you just look at the expression, not an integer exponent, it's not a polynomial. It's not a positive exponent, so not a polynomial. This one, you might be tempted to say is a polynomial, but it is not a polynomial because of this. And that's a new type of function that we'll learn later. That's an exponential function. So even though these are all integer powers, because it's 2 to the power of x squared, it's no longer a polynomial. Just be careful. I guess I should also say when I give my definition that x cannot be in the exponent of something else. So, but this almost looks like a polynomial, but this is not really a polynomial. Okay, so graphically, polynomials, we went through all the properties. They're smooth. Let me just make sure it's continuous. For all real numbers, right? So something like a linear graph, right? This is a polynomial. F of x is equal to 2x plus 1, or 2x, something like that. I don't know. Linear graph goes from negative infinity to infinity. Has no sharp corners. Okay, so something like the absolute value function, which is right here, cannot be a polynomial. Number 3, it has at most n real zeros. So what that means is it has, another way of saying that, a finite number of zeros. So something like this, where it keeps crossing the x-axis like a sine or cosine function, is not a polynomial because it keeps going through it. Oh boy, I gotta make sure I don't go out of the camera. It has at most n minus 1 turning points. It's almost goes hand in hand with number 3. So, for example, y equals x squared is a polynomial, and it looks like this. It has one turning point. So n minus 1, n is the highest power, so it has n minus 1 turning points. It increases or decreases without bound as x goes to positive infinity, so increases or decreases as x goes to infinity and x goes to negative infinity. So that just means it doesn't have any horizontal asymptotes either. So you won't see something like this. Well, I don't know what function that would be, but the fact that it goes flat like that, not a polynomial. Not a polynomial. All polynomials always are unbounded, is the way that an analyst would put it. So those are the graphs properties that we went over. All right. So now with those definitions and with the understanding of the fact that we can factor polynomials completely into at most n factors, where the factors are all the number of times it crosses the x-axis, assuming they're real factors. We can pretty much figure out what a polynomial would look like just from knowing the degree and the number of zeros and things like that. We can build the polynomial. Here they're going to ask us about the graph, and they don't quite give us enough details to get the exact expression algebraically, but here's how you get the graph. So it has odd degree, has a positive leading coefficient, and these are negative 4, 1, and 5 over 2. So negative 4 comma 0 is right here. So I know the graph is going to go through that point because it just tells me it's 0. 1 right here, and 5 over 2 is slightly larger than 2, so that's right around here. Odd degree. So remember, I went over the n behavior. If it's of odd degree and it has a positive leading coefficient, then it has to have this basic shape. Okay? Where the middle part, I should draw something more like this. The middle part, we don't know exactly what's happening in the middle, but we know that on the left it goes down and on the right it goes up, and we're not sure what happens in the middle. So with this one, it has to be going like this through here, and then it has to be going like this over here. And then I'm not sure what happens in the middle. Since it's an odd degree, and these are the only zeros, then it has to be of degree 3. I'm sorry, I shouldn't say that. It could have multiplicity there. So it's of odd degree, so I know it has that shape, and I can draw the following. I could draw it like this. It has to be smooth and continuous, so just connect everything. It just kind of intuitively, you should be able to see that. So I can almost write the expressions. This is the graph. The issue is that we don't know what these points on the y-axis are. We only have these points on the x-axis. Right? We only have those points on the x-axis. So we can almost write the expression, because I could write this as x minus that number, which is negative 4, so this becomes x plus 4, one of the factors, x minus this number, 1, and x minus that number over 2. And then there might be a number in front, which I'll call k, a constant in front. The only way we could figure out what that constant is that if they gave us a point that was off of the x-axis. Yeah, so because we don't know how much the graph is stretched. It may have a vertical stretching that's happening. So just because a graph is vertically stretched, it could still have the exact same zeros, but it's just increasing or decreasing faster than if it wasn't being stretched. So we don't know what this is. That's the only detail we're missing. And they would have to give us one point, like maybe say this point right here. And if they were to tell us what that was, then we could figure out exactly what this polynomial is. So that's how you figure that out. The homework is there, and I want this by Tuesday. Shouldn't be too much. Tuesday at the end of class. So there's something we have to go over right now, which is division of polynomials, because these later problems are about that. It's not too complicated, it's just if you haven't seen it before, it might be a little bit weird. Okay, before we do that, let's just start going over some of these problems. I'll go over the odds. So you have in the book numbers 1 and 3 I'll do. So it says negative ax cubed, and what I'm supposed to do is I'm supposed to match these functions with one of these four graphs, A, B, C, or D. So that's what I'll do. I know the end behavior, right? Even functions have end behavior like this or like this. Odd functions have end behavior like this, depending on what the sign is in front. So for number 1, since it's a negative sign, it's an odd function. An odd function with just a positive sign will look like this, but now it's going to be flipped. So 1 is B. 3 is an even function with a positive, so I know it's opening up. So opens up. So it's D, so 3 is D. And that's how you figure those out. Simple enough. Okay, numbers 5 through 8. So we're supposed to look at these and be able to list all the zeros and turning points and the left and right end behavior. I think this is good because you kind of know what they're asking for, like what does it do as x gets bigger and bigger and bigger, but this helps you kind of write it in a very formal way, which is good, because sometimes it can be a little bit hard to figure out how to express that. So number 5, they want me to write the real zeros, so I have this graph here, 1, 2, 3, 1, 1, 2, 3. And it's going like a dat. Alright, so the real zeros, first of all, we should be able to tell right off the bat this is an even polynomial. It has 2 zeros, so it has to be quadratic. Yeah. So p of x is going to be equal to, well, I'm sorry, they don't want us to write the function. So the zeros are 1, negative 1, sorry, right at it, negative. Okay, that is really bad. I need to make sure I'm in the camera. I apologize. I can't edit that out. Goodness. All right, so the real zeros, again, this is my function here, and this is a quadratic if I look at it, and the real zeros are going to be at negative 1 if I look there, and positive 3. Zeros at 1, at negative 1, and 3. Okay, the turning point is going to be right here, which looks like 1, 4. So turns at 1, 4. Yeah, that's it. Oh, end behavior. Okay, so you would say for end behavior, as x goes to negative infinity, so as it goes to the left, as x goes to the left, what direction is the graph going, up or down? And you would say f of x goes to negative infinity. Okay, that's the first part, but there's two sides to the graph, so you have to talk about both sides. So the second part, as x goes to positive infinity, f of x goes to negative infinity. So as x goes all the way to the right, the graph is going down. So negative infinity. That's what that notation means. It means what direction is the graph going as x goes either to the left or to the right. So for number 2, I said x is going this way, the graph is going down. That's all that this means right here. As x goes to the right, the graph goes down. That's maybe how you read it in English. Let's try number 7. I'm going to try to keep the whole thing on the screen this time. I appreciate your patience. Number 7. Okay, so we have this thing happening here. Okay, and then this is at -4, or +4 rather, and that's it. So this is a good, I like this example because if we were to look at these two different zeros, we would notice something about this one, and that's that it would be a perfect square. This would be a squared zero. It would have even multiplicity, and this would have odd multiplicity because just the fact that it goes through, and then this one turns there. So the zeros are at -1, -2, right there, and then 1. And they don't talk about multiplicity yet. I guess we'll get into that later. Turning point turns here, which looks like -1, 4. And then it also turns at 1, 0. It turns right at that 0. All right. The end behavior. So as x goes to the left, that's how you read that. As x goes to the left, what is the graph doing? It's going down. So f of x goes to negative infinity. Number 2, as I take x to the right, as x goes this way, then f of x goes to positive infinity. I see the graph goes up. That's how you do those. All right, number 9. Explain why each graph is not a polynomial function. These are excellent. So we have this thingy. This is a very interesting graph, very, very interesting function called the Gaussian, or a lot of people call it the bell curve, and it just has a bunch of interesting properties in probability theory and things like that, and statistics. But it's not a polynomial. And why might it not be a polynomial? Well, there could be several reasons. One right off the bat that I can see is that the end behavior of the graph is not right. A polynomial must be unbounded, meaning that as x, it's doing something like this, right? As x goes to the left or right, the graph goes to infinity or negative infinity. It never stops growing or decreasing. So that's what it means by unbounded. Here you could see the graph has an asymptote. So maybe a simpler or more concise way to say that is a polynomial should have no horizontal asymptotes, where this one does, which is right at the x-axis. So that's one problem with it. I think that's basically the only issue with it, is that it's bounded. So not a polynomial because of end behavior. In other words, as x goes to negative infinity and x goes to positive infinity, f of x does not go to infinity. A much more concise way of saying this whole sentence here is just that f of x is bounded. The only case for which this is okay, because this is going to be if it's a constant function. So I guess there are definitely polynomials that can be bounded, but they're constant functions. I don't think it's true in general for other polynomials. So if you have something like this, f of x equals 5, whoopsies, 5, then yeah, this is a bounded function. It goes through there and it never goes up or down. But that's still a polynomial by the most general definition. So yeah. Okay. Let's see, number 11. Number 11 is going to have the same issue. There's might be a few different reasons. There are a few different reasons, actually, I can already see. So it's doing this thing. It's like this wavy, increasing function. One of the things is obviously, again, this is oh no, this is unbounded, so that's okay. Yeah, the only issue with this one is that there are infinite turning points. So a polynomial is supposed to turn a couple times and then just do what it's going to do. This thing keeps turning and it's not supposed to do that. So it's tempting. This almost seems like it's a polynomial because we haven't talked about this case before where it could just kind of keep going up and down. And it is increasing. So technically, as x goes to infinity, f of x is going to infinity. So you might almost say this could be an odd polynomial. But the fact that it keeps turning like that, it goes up and down and up and down and up and down, not a polynomial. So, okay. Now, number 13. We're supposed to list the zeros of this polynomial function. So it gives us p of x is equal to x times x squared minus 9 times x squared plus 4. All zeros. And now that word all is an important word because there are certain zeros, as we've learned, that are not real. So something like this, this is some version of the quadratic function. It has a zero, but it's not a real zero. It's a complex zero because it never touches the x-axis. So they're asking for every single zero here. So I want to factor this completely, in other words. So I look and I say, well, this can't be factored anymore. This can be split up because it's a difference of squares. So I can write it as x minus 3 times x plus 3. So that's this one here, became this. This is factorable, but it's not a real factor. So this has two complex zeros, and they are x plus 2i and then x minus 2i. Because x squared plus 4, if you were to maybe use the quadratic formula on that, maybe that's a way you could do it. If you can't just kind of see it, you would get these as your two answers. You would get complex numbers. So that's the easiest way to do it. So all of our zeros are going to be 0, 3, -3, -2i, and 2i. Or the book might write it 0 plus or minus 3 and plus or minus 2i. So you have 5 zeros. So it's a polynomial of degree 5. All right. 15. X plus 5 times x squared plus 9 times x squared plus 16. Again, all zeros. So this and this don't look factorable because of the plus. It's no longer a difference of squares for real numbers, but it's a difference of complex squares. So I write this the same way, and this is going to have x plus 3i times x minus 3i. So I guess a helpful tip is that if you see a square and a positive like that, it's still a difference of squares, but they're complex squares. So just remember there's going to be an I there. Whereas if I were to have something like x squared minus 4, this I know factors into x plus 2, x minus 2. But then once I put that there, this becomes 2i and this becomes 2i. So that's what I was trying to say. This becomes x plus 4i, x minus 4i. So all of our zeros, negative 5, negative 3i, 3i, negative 4i, and 4i. Or, more condensed, negative 5 plus or minus 3i plus or minus 4i. Again, this is a polynomial of degree 5. Okay, now polynomial division. This is polynomials are kind of the building blocks of a lot of other functions. There are certain functions that can't be written as a series or in terms of polynomials, but there are certainly a lot that can be, and that's why they're very nice to study. They're just well-behaved things, and you can divide them just like you can divide integers, and you can have a remainder and all that stuff. And in fact, even the process of polynomial division is a lot like how you would do long division. So if I were to do long division, if I were to do something like 264 divided by 4, then I would say, well, 4 goes in here 6 times, and then I would multiply, and I would have 24 minus, and then I would get, subtract the 2, I'd get 24. This would go away, and then here I would have, well, that's 6, so again, I get 24, and I would have a remainder of 0, and I'd be happy because that would make, I'm sorry, again, I was out of the screen. Getting a remainder of 0 was something we liked to do. Occasionally, though, that doesn't happen. If I were to change this to 4 divides 265, then that becomes 66 again, but then I have a remainder of 1. So I would say 265 is equal to 66 times 4 plus the remainder. Well, we can write polynomials that same way. If I have something like number 17, 4m squared minus 1, and I want to divide that by m minus 1. Alright, well, there's a way to do this, and I can write it very similarly. My final answer might look a lot like this. So let's try it. I write just like I would divide integers. I would write the biggest polynomial on the inside, like that, and I would write the smaller one on the outside. And I say, what do I need in order for this to match this so that I can subtract them and get rid of the first term? And I need a 4m. So I multiply and I get 4m squared. And I subtract, 4m squared minus 4m. So then I'm subtracting these, and this goes away, and I end up with 4m minus 1, right? Okay, so then I want to add 4, because the idea is to get rid of this. So 4 times m is 4m minus 4, subtract. Negative 1. Oh, this is negative 4m. So this should be negative 4. Okay. Plus 4. So we're going to get a remainder there. So what that means is now we have a remainder of 3. What that means is the original 4m squared minus 1 can be written as the product of this and this, 4m minus 4 times m minus 1, apparently, if I did that right, plus the remainder, which is 3. Plus the remainder, which is 3. So that's how polynomial division works. Very similar to long division. I'll do a couple more because it's a tricky concept. Number 19. 6 minus 6x plus 8x squared divided by x plus 2. So again, our smaller polynomial goes on the outside and our larger polynomial goes on the inside. Write the highest power first, ax squared, and then write it in descending order just to make life easier, plus 6. How do I get rid of this? I need an 8x. So multiply, we get 8x. Subtract, oops, 8x times 2 is 16x. Okay? So subtract these two, they go away. Negative 6x minus 16x gives me negative 22x, and I bring down the 6. Alright, minus rather 22. So 22, negative 22, so negative 22x minus 44, and I'm going to be subtracting this, so this goes away. 6 plus 44 is going to be 50. So that's my remainder. So then I say, okay, well, 8x squared minus 6x plus 6 can be written as this times this, 8x minus 22 times x plus 2 plus the remainder. And that remainder is going to be important when we start talking about graphing rational functions, because remember, rational functions are just the division of two different polynomials. If there is a remainder, that will create what's called an oblique asymptote if the remainder is of degree 1. So that's how you do that. That's two examples of how to divide polynomials. I don't want to be redundant and do more. That's using long division. Under certain cases, there's a faster method called synthetic division, which is nice to use, and I'll do number 25 to illustrate that. So synthetic division, all you got to do is write the coefficients. So here they're asking us to do x squared plus 3x minus 7 divide x minus 2. Okay, well, I'll start out by writing it the way we've been doing it. So x squared plus 3x minus 7, that's going to go underneath this thingy, and then this goes here. But instead of actually like doing all that multiplying and figuring out what I need, I can just write the coefficients underneath here. So they like to use a straight bar to show it's synthetic, I guess. The coefficients here are 1, 3, and negative 7. Okay? Then here I just write whatever the root is. So what does it take to make this 0? 2. If I plug in a 2 into there, this expression becomes 0, and that's what I write right there. Then you always bring down the first coefficient, and you say, okay, now instead of subtracting, I'm going to add this to a multiple of this. So I would multiply by negative, oh, I'm sorry, this times this would give me 2, and I add them together and I get 5. And then this times this would give me 10, and I add them together and I get 3. That's how that works. So you bring down the first power, then you multiply this with this to get this number, add these two together to get this number, multiply this and this to get this number, add these two together to get your final answer. And then you kind of keep that pattern if I had more numbers. So what does this mean? Well, this is the coefficient of my quotient. This is the first coefficient of my quotient. So it's going to be x and then plus 5x, oops, plus 5, sorry, plus 5. And then the remainder is 3. Here's my remainder. You see? So this is my quotient here. So this times this would give me that plus the remainder. So what they're finally looking for is you to be able to write x squared plus 3x minus 7 is equal to x minus 2 times x plus 5 plus the remainder. So synthetic division looks, I don't know, in this problem it maybe looks like it takes the same amount of time, but it can be a little bit quicker. It's just less writing, so it's nice. A lot of people tend to like synthetic division better. And that should get you through number 30. And I'll do one more. I'll do number 31. Number 31. And it says x to the 18th minus 1, x minus 1. So the question's asking us to determine whether the second polynomial is a factor of the first without dividing or using a synthetic division. And it says evaluate directly and use the factor theorem. So the factor theorem just says that if you have some polynomial like p of x equals whatever, if some number, if r, but let's not use r because we don't like letters, let's say 23.1, okay? If this is a 0, then p of 23.1 obviously equals 0. But more importantly, this is a factor of the polynomial. So that means this polynomial can be written something like x minus 23.1 times a quotient, which we don't know, plus a remainder, which might be 0. But that's just like we've been writing our polynomials as products and then plus a remainder. That's what can happen here. But what these are is these factors show us what the zeros of the polynomial are. So they're telling us, well, is this a factor of this? All you got to do is look and say, well, this is a 1. So what I need to plug in to get 0 here is a 1. So I'm claiming that 1, by saying this is a factor of this, I'm claiming that 1 is a 0 of this polynomial. So I should be able to say, well then, this, when I plug in 1, should give me 0. And obviously, it does. So x minus 1 is a factor. That's how that works. All the factors show you what the zeros are. So if they tell you, well, this is a factor, then you know that if I plug in this number, then that's a 0. So that's should get you through the homework pretty well. Good luck.